Perfect. So then I will start. And as was mentioned, this is the practice presentation for my PhD defense. And in general, the title that I selected is Machine Learning for Medical Applications, Learning with Limited Instances. So this talk is divided in three basic sections. First, I will go through machine learning and its assumptions, take this as machine learning 101. Then I will talk about the core of the dissertation, how to deal with limited instances. And I'm going to talk about three different ideas in here. The first one is going to be about probabilistic labels for classification tasks. Then I'm going to talk about the use of machine learning and epidemiological models for the forecasting of COVID-19, the number of infected people. And at the end, I will talk about style transfer for domain adaptation. Now, this may look like three completely different ideas, but as you will see, hopefully during the presentation, is that they are actually very, very related. And all of them have in common the fact that they are dealing with limited instances. And then at the end is just the conclusions. So let me start with machine learning and its assumptions. The main objective of machine learning is to make predictions in previously unseen instances. That is the main idea. That is what machine learning was designed to do. For example, we can have an ultrasound image, in this case of the hip of a baby. Then we want to input this image into a classifier, and then we want the classifier to tell us, oh, does this person have dysplasia or not? Classification task. A second example might be, let's take again the same image, but now we do not want a binary decision. We might want to identify some anatomical structure. So then we go to a segmentation algorithm. And then the output is going to be a mask reflecting the anatomical structures that we care about. In this case, is the bone that is in green and the bone that is in yellow. A third and final example is, well, what if we want to make predictions, for example, in a time series? Now it is not a classification task anymore. It is more like a regression part. So for example, we can see the evolution in the number of infected people of COVID in Canada, and then we are at some point in time, and then we want to make the prediction K weeks into the future. How many people do we expect? So then we make this prediction marked with an X, and we wait, and then we see how good our prediction was, and then we can measure how good our predictor is. So in general, these are like the traditional machine learning tasks in supervised learning, classification, segmentation, that is like a subset of classification, and regression, where we want to predict a real value. Now, how do we make these predictions in previously unseen instances? The traditional supervised machine learning paradigm starts by collecting a training dataset. And a training dataset is simply a collection of inputs, X. It can be an image, it can be a time series, it can be a vector, it can be anything. And the target, that is the quantity or the class that we want to predict, that we call Y. Then we input this training dataset into a learning algorithm. And this learning algorithm outputs a predictor. We learn the parameters, usually of a parameterized model. And then we use this model with a new instance that we have never seen. And then the predictor said, well, this is my prediction. This is the class, or this is the real value that I believe is associated with this new instance. Now, this paradigm is making some implicit assumptions when we are working with these machine learning tasks. The first one is that the dataset D that we are collecting and the instances where we want to apply the output classifier are generated by the same probability distributions. And this is just a fancy way of saying that they are similar, that they are similar. The second assumption is that our training dataset D has enough instances to learn a good predictor. We have enough data to learn something. A third assumption is that Y is reliable and objective. Usually in machine learning, an external source gives us these labels, and then we use them to learn the mapping from X to Y. And it turns out that these three assumptions are often not valid in tasks related to medicine. So when we try to apply machine learning in medicine, some typical characteristics are that first, we have relatively few labeled instances for training. In images or in tasks that deal with natural images, we might have access to millions or billions of images. And the same with text. We have millions of documents. We have Wikipedia. We have web pages. Now, in the case of medical instances, they are relatively few compared with these other tasks, maybe a few hundreds, a few thousands. Then the instances, they can come from different distributions. This can be, for example, images acquired with different scanners, or we might be analyzing people that come from different populations and therefore they behave differently. So this is with respect to the assumption that the training and the test data are similar. Well, it is possible that that is not the case. The third one is that we have to deal a lot with subjective labels. Usually when you show the same challenging image to different experts, they come with different opinions. So then the label that we use for learning is not 100% reliable. Now, it has one advantage, and the advantage is that we have lots of background knowledge. So that means that we believe that we know a lot about medicine, and maybe the machine learning algorithm doesn't have to learn everything from scratch. Maybe we can leverage this medical knowledge and help machine learning to learn more efficiently in the absence of big data sets. So that is the main idea, to compensate for the lack of data. So then, the focus of my research, and specifically this dissertation, is how do we adapt this machine learning framework to work when we do not have giant data sets, or we don't have enough instances to cover all the spectrum that we can find on the test set. So there are three ideas that I want to talk about. The first one is to encode the medical knowledge as probabilistic labels. So in this diagram, we are going to be modifying this Y. And as we will see during the presentation, this gives an advantage. For example, for the case of hip dysplasia, if we use a traditional paradigm, we can have a 74% accuracy in identifying this condition. But with the idea that I'm going to talk about, we can boost this to 83%. By the way, the baseline was 50% in this case. And then we tried it with fatty liver, then we tried this with glaucoma, and then we got very positive results in all of them. So it turned out that it was like a good approach. The second idea is how do we incorporate this external knowledge, not in the labels, but now directly in the learning algorithm. And here I am going to talk about one approach that we use for predicting COVID. And we call it similar because it is machine learning inside the SIR model. I'm going to give more details about this. But the main idea is that we make a combination of epidemiological models, machine learning models, and we track the government policies in order to predict new infections 1 to 4 weeks in advance. And we incorporate this to a graphical model that I'm going to talk about later. And then we got state-of-the-art results. The third idea is to reduce the discrepancy between the train and test set. So now we are going to be dealing with the feature vectors, both in training and in test. There are different ways of trying to reduce the discrepancy. In this presentation, I'm going to mention only one of them in domain adaptation. And we will see that when we have an input image like this, if we forget or if we take like the implicit assumption that training and test come from the same distribution, then we will have segmentation results like this. But if we acknowledge that there is a difference and then we make an effort to correct them, then we can end up with much better segmentations. So these are the three ideas that I want to talk about during this presentation. So let me start with the probabilistic labels for classification. And remember, we are going to encode the medical knowledge directly into the labels for this case. So the performance task is, again, we have the ultrasound image, we input this to a classifier, and then we want the classifier to predict the probability that the person has some disease. Traditionally, what we are going to do is we are going to collect a bunch of images, and then one expert is going to tell us all of these images are healthy, are from the class 0. And then we are going to repeat the same for images of people who have this condition, hip dysplasia. And then we are going to label them class 1. Since these are images, the most common approach nowadays is simply to input this into a convolutional neural network where the targets are 0 or 1. And then we choose a loss function. In this case, is the cross entropy. And then we optimize the cross entropy. The term in blue is the label 0 or 1. And the term in red is basically the prediction made by this convolutional neural network. And then we try to minimize this quantity. So when we use this is the performance that we got for hip dysplasia, for fatty liver, and for glaucoma. So this is the traditional method. This is the first thing that we might try. Now, the common problem is, how do we boost this performance? Or why is not much better? And usually the answer is, well, we do not have enough data. We do not have enough data to improve the performance of this algorithm. So then the idea that we proposed is to use probabilistic labels and then give more information per every instance. If you are unable to collect more data, then give more information per every piece of data that you have. So traditionally, Y is going to be the case and control, 0 or 1. But now what we are proposing is that these labels are going to be numbers between 0 and 1. It's going to be a real number. And not only any real number, it's going to be the probability that some instance belongs to the class 1 or belongs to the class 0. So for example, if this person has dysplasia, then the label is 1, 0. So what we are proposing is, no, don't use that label, use the label 0.6, 0.4. This image has a 60% probability of having dysplasia, but 40% probability of being healthy. Now, the main question is, how do we get these labels? Where do they come from? And this is where we leverage the medical knowledge. Basically, we are going to start by understanding how the medical experts are diagnosing this condition right now. So we identify what are the relevant features, and then we go and extract manually those features from the images in our training set. For example, for hip dysplasia, there are two quantities that they care about. They start by identifying the bones, ilium and acetabulum, and then they measure the angle between them. And then they go for the femoral head, and then they measure the quantities D1 and D2, and they care about the ratio of D1 and D2. So these two metrics, the ratio and the angle, are the relevant metrics for identifying hip dysplasia from ultrasound images of the hip. So if we extract this alpha and ratio from every image, then we can build a graphical model on top of that. So we know the hard or the categorical label given by the expert, dysplasia or normal, and we also know the angles. Then if we build the graphical model and then we put probabilities, then per every image, we can estimate the probability of belonging to any of the two classes. So let me go to this example in more detail. For example, this image here was diagnosed with dysplasia. So we go and we measure the angle alpha and the ratio of D1 and D2. This is called coverage. This is why it has the letter C in there. So Let's say that we have an angle alpha of 41 and a coverage of 0.23. So then we go into this scatter plot, and then we put a dot in there. This dot is the representation of the image. Angle 41, coverage 0.23. And then we repeat the same for all the images that are diagnosed with dysplasia. So we end up with many dots. Every dot is one image. And we do this for all the dysplastic images. And then we repeat the same for all the images that are normal. So then we have our scatter plot complete. Now, the next step is to put a probability distribution in top of the orange data and in top of the blue data. And in this case, I selected a Gaussian just because it looked good enough. It can be approximated with any other distribution or a mixture of distributions. If we want, it can be a mixture of Gaussians, it can be a Poisson, it can be whatever the person wants to use to model this distribution. And then we have the probability of X, and this X is going to be the image given, this X is going to be the image, the angle and the coverage pair given the class. And we have the model, the blue model, and then we have the orange model. And then we can simply use the Bayes theorem to compute the probabilistic label of every image. Because if we know these values of alpha and coverage, then we can compute what is the probability that Y is equal to 1 given X, that is the angle and the coverage. And this requires 3 terms, basically. Basically, it's only 2. It is the probability of X given Y, and this is the Gaussian model that we proposed. So we just have to evaluate that. And then we require the prior probability of Y equals to 1 and Y equal to 0. Given these things, then we can simply compute these multiplications and then the division, and then we get the probabilistic label of this image. Something very important, these priors are not the probability of Y equal 1 and Y equal 0 in our dataset. These are the probabilities that we expect to see on the field where we deploy this, which means that usually these probabilities are extracted from literature. For example, the incidence of hip dysplasia can be 0.1% or 2% of the population. Well, the priors come from there, not the proportion of cases in the training data. Now that we have our probabilistic labels per every image, then we repeat and we do the same thing as always. We take the image, we have this input, we put it into a convolutional neural network, then the label is no longer 0.1, it's 0.03 and 0.97, and then we train the model. It turns out that we can still use the same loss function. The way we can use it is a little bit mathematical, but the thing is that the same cross entropy also works with labels that are not categorical, as long as they are numbers that add up to 1 and are positives. So now let's see the advantage. Before we had this 74%, now we go to 83% by applying this trick. In fatty liver, it was a statistical tie. It was like 90 point something versus 89 point something. It's basically the same performance, which was very good indeed. And in the case of glaucoma, we went from 55% to 77%. Now, these probabilistic labels have other nice properties. I will not go into that detail. But this is like the first idea of how do we incorporate the external medical knowledge into the machine learning framework. The second task that I want to talk about is the machine learning for the forecasting of the people who was infected of COVID-19. So as a reminder, now this part is going to be how do we incorporate the external knowledge directly into the model. And in this case, we're going to use a probabilistic graphical model. So the objective is to predict the number of newly infected people 1 to 4 weeks in advance. For example, if we are in Canada, we can be monitoring the evolution of the number of infected people over time. And then we want to make this prediction 8 weeks into the future. We make the prediction and then we compare. This is the game that we are playing in here. How do people usually do that? And there are many variations of this model, but this is the backbone. This is the basic version of this model. They have something in epidemiology called the SIR model. S is for the susceptible people, the people who can get infected, but at this point they are healthy. You have the I, that is the people who is infected right now, and then you have the R, that is the people who is removed from the system. They can be removed because they died, or they can be removed because they recovered. And then the people are doing transitions between these groups. For example, if someone is susceptible, he or she is healthy, then they either remain healthy or they can move and become infected. If they are infected, they can continue being infected, or they can move to the removed category. Now, this model assumes that once that somebody is removed, then they are out of the, they stay in the removed category forever. This model doesn't allow the possibility of reinfection. So there are two important parameters in this model. The first one is called beta, that is the transmission rate. And the second one is gamma, that is the recovery rate. Basically, this transmission parameter beta determines how quickly people move from the susceptible to the infected. And this is why this model with differential equations has a negative sign, because people go out from the susceptible to be moved into the infected. Then the infected people, the people who come out of the susceptible, go into the infected. But we can also have people who goes out from the infected and move into the recovered. And this is what the recovery parameter is modeling, this theta I. So it's negative because they are going out. This one is positive because they are going in. And of course, the remaining term is simply the people who went out of the infected. Now, how do we work with these SIR models? What we usually do is we are given a sequence of states, x1 to xn, where this x can be the number of susceptible and the number of infected. But by the way, the SIR model assumes that the size of the population is constant. Therefore, if you know the size of the population, and then you have the number of susceptible and the number of infected, then the number of removed is simply the population minus S plus I. This is why we only require two states. So given a sequence of states, for example, in this case, this curve is for the number of infected. If we have also the curve for the number of susceptible, then we can solve the following optimization problem. We can find the parameters beta and gamma that best fit the data. And by best, we mean that minimize the mean squared error, or the sum of the squared error between the actual values and the values predicted by the SIR. This x hat is obtained by solving these differential equations, or by solving the discretized version of the differential equation. So then we can find the parameters, beta and gamma, that best fit the data, very traditional task in machine learning. And then we can evaluate how good it is to explain the data. Forget about predictions at this point. Let's test on the same training data and let's see how well this model does. Because if it doesn't work on the training data, then it's not going to work for evaluation of the performance. The resubstitution error is an overestimation of the performance. So let's look at the entire data at these 56 weeks of data. Let's learn the parameters. And once that we have the parameters, let's go back in time. Let's assume that we are on the week 16. Let's use the parameters to make the prediction. And yeah, to make the prediction. And this is our prediction. Because yeah, it looks like an extension of this part. But then we compare with what actually happened, and it turns out that the reality is that it went up. And then we keep doing this for all the weeks in the dataset. So we end up with a curve like that. So even when we are testing on the same training data, the model is struggling to actually make accurate predictions. Remember, this should be an overfitting case, which means that the predictions should be very close to what actually happened, which is not happening here. So now the solution that we proposed, it goes into different stages. The stage number one is to change the parameters over time. So for example, instead of learning a single beta for the entire time series, we are going to divide this time series into different subparts, in this case, every 10 weeks, for example. And then we learn the parameter beta and gamma that best fits these first 10 weeks. Then we learn a second beta and gamma for the next one. And then we keep doing this over and over until we learn a different parameter per every subset of the training data. And then we repeat the experiment. And now we have the graph on the right. So again, this is the resubstitution performance, but even here we can see the difference, that if we start changing the beta and gamma over time, then we can actually explain the data almost perfectly, while the traditional SIR model cannot do it. So this is like the first idea that we are proposing. Let's change these parameters over time. Now, of course, this has nothing to do with predictive performance. The real question that we need to be asking is, if you have only access to the first 30 weeks of data, or if we are in the week number 30, then let's measure the beta 1, beta 2, and beta 3 from the past. But then what we want to do is to predict the value of beta 4 and gamma 4 without looking at the data, because this is what we care about, the prediction in the future. So then by obtaining these betas 1, 2, and 3, can we make the prediction of beta 4 and the same for gamma? And this is the first part of the similar model. We take the data from the 3 previous weeks that we can find by solving the optimization problem. And then using these 3 points, then we go and predict the point number 4. And then we do the same for gamma. Take the gamma of the 3 previous time points to make the prediction of the next one. For this particular case, we chose to do the probabilistic version of a simple linear regression. It turned out that this worked very, very well. So this is the model. This is just linear regression with probabilities. So now that we have our predictor for beta and gamma, then we can use those predicted values along with the last time point that we have access to make the prediction of the next state of the SIR model. And then by just comparing the number of infections in the new state and the number of infections in the current state, we can get the difference. And this is just like a deterministic operation, the difference between these two. And this is the number of newly infected people. So for example, if we have 100 infected today, and my prediction is that the next week we are going to have 120, then how many new infections will we have? Well, 120 minus 100, 20 of them. And this is how we make the prediction of the new infections. And it works quite well. So for example, imagine that we are here at the week 15. Then we take the beta of the 3 previous weeks. We predict the new beta and gamma. And then we use that probabilistic model. And before that, we have 2 options. We can predict, we can first say that, the next week we will see whatever we see on the previous week. Then we use the similar model to make our actual prediction, that is the orange in this case. And then we compare with the reality. And it is working very, very well. Now, let's look at a different example. Now we are on the week 23, well, 22. We repeat the same experiment. We can either predict that the next week is whatever I see in this week, or we can use the similar model and then make a prediction. And look how this prediction is completely valid, because the trend is going up. So then we have to keep assuming that this will continue going up. But what happened in reality is that the thing went down. So when we make the predictions on the entire year, we see something like this. The blue line is the actual ground truth. The green model, it is predicting the same as the last observed week. This is why we call it slow. So we predict that the next week is whatever we saw in the current week. And the orange one is the similar model, that is the SIR that changes over time. So we can see that we have a horrible peaking here. And the reason is, why is this happening? And well, it happened because there is a change of trend. So if we were able to identify with this change of trend is happening when it goes from going up to going down, then we could switch to a different model, for example, to the more conservative, slow model. But the problem is, how do we identify when this change of trend is going to happen? And it turns out that this is closely related to the policies that we have. And this is very intuitive information. This is why we incorporate this intuition into our model. If the government policies are relaxed and there are no policies in place, then we can expect the number of cases to go up. But if suddenly they establish strict policies, like a stay-at-home requirement, then we expect that the number of cases will go down. Not immediately, because we know, well, the first variant of the COVID had an incubation time of 2 weeks. So then we expect to see the results maybe between 1 and 3 weeks into the future. But then if we observe the change of policy today, we might make the prediction that the trend is going down into the future. And this is what we did. So then we observe the change in policy during the last 3 weeks. And then based on that, we estimate what is the probability of observing a change in the trend. And by the way, this is data that we have to manually encode. You can think about this as a Bayesian prior, because we don't have a data set for this. So we had to encode our knowledge in terms of probabilities. Once that we have the change in trend, then we can go and use the similar model that we had before, the linear regression, SIR, all of that. And this is the result. Then there is no horrible peak, because in fact, we identify at this week, there was a change in policy. Then during the next time points, this one, and this one, we are making the predictions of the green model. Oh, sorry, this one, and this one. Because we were expecting the change of trend. After that, we expect the change of trend to be over, and then we can continue following the new trend. And as you see, now the red curve is doing much better. Then there is another change of policy in here. The model becomes conservative, and then catches the new trend, and then starts predicting again. So it is doing a very good job in this case. We actually compared the performance of this model with many other models that were submitted to the CDC in the US. And we are, depending on how you look at it, we can be either second place in absolute terms. The reality is that this is a statistical type, because there is a very big variance in the prediction. So statistically, we are tied, or in absolute terms, we are like in the second place in performance, which is actually a very good result. What was impressive is that this dotted line in here is the same as the last week. So basically, most of the teams were not able to beat this very simple baseline, which doesn't mean that they don't know what they are doing. This only says that this baseline is actually very, very strong, which makes sense. For example, if we see 100 cases today, it's not a bad assumption to assume 100 cases the next week. It's going to be around that number. So it is actually a good baseline. The last idea that I want to talk about today is style transfer for domain adaptation. This goes into the input vectors, the discrepancy between the training and the test set. And the idea is to reduce this discrepancy. So let me say what is the problem setting here. Imagine that you want to build a classifier that distinguishes between the blue and the red figures, the squares and the triangles. So you have your training set, then you build your classifier. It works very well, even if you did the things properly, like separating the training set into training and validation, or if you do cross-validation, even if you do the things properly, you can have a classifier like this. But it turns out that the data on the test set simply is different. For many reasons, it can have a different distribution. So then your classifier that works well on data from the training distribution doesn't generalize to the test distribution. So then the idea is, what do we do about it? And let me talk about a real example here. This is the input, an ultrasound image of the hip. And then we want to perform the segmentation of the red bone and the blue bone. These two things that you see in here. So it turns out that we have a data set, a training data set for the scanner A, but the test set is from the scanner B. So one is a linear probe, the other one is a conic probe. So what is the effect of that? That when you train your segmenter and then you test it on a new image of the linear probe, you have a very good segmentation. But when you take it to the conic probe, then the segmentation is not nearly as good as the original, because they come from different distributions. This is the example of the blue square and the red triangle. The distribution is different, so it doesn't generalize. So then the step number one is to formalize the problem and think about covariate shift, but with different assumptions. The joint probability of X, that is in this case the images, and Y, that is the segmentation mask, is different in A and B. But different how? Well, the assumption is that the conditional probability of Y given X is different between A and B. The marginal probability of X between A and Y, A and B is the same. We are also assuming that the probability of Y is going to be the same. We can assume that probably the size of the bones in babies is not going to dramatically change between A and B. But we assume that there exists a function f of x with some parameters theta A and theta B, such that when we apply this function to the data from theta A and theta B, then the distributions become the same, both the conditional and the marginal. So one way of looking at this graphically is this diagram. Y is the labels, Z is a common space that is latent because we don't observe it, and XA and XB is the observed data. So the only thing that we were saying in the past slide is that there is a way to map from XA to Z and from XB to Z. And then if we build the classifier in Z, then we are done because now they have a common distribution. A different alternative is to map from XA to Z and then from Z to XB, and then build the mapping between Y and XB directly. And actually, this is what the idea of style transfer is doing. So there are networks that are already pre-trained to make an image look like the style of another. For example, we have this bridge on the left, we have a painting on the middle, and then if we make the style transfer, this is what we get: the content of one and the style of the second one. So then we started exploring the idea of doing exactly the same for these images. What if the content image is the image from the linear probe, and then the style image is the one on the test set, actually, of the conic probe? And then we create the following. We transfer the style of one to the other. So now the texture looks more like the image on the middle, but we can see that the content is basically the same. The structural information of the bones is very similar. For example, look at this part over here that is actually here. Then this bone in here in the middle is also in this part. So the content is basically the same, the style is different. And there are ways to formalize this notion. I am not going to go over them in here because it's a lengthy discussion. There is a formal way of treating that. So what is the effect of making this? Well, take the inputs on the left. When we train a model with the original data, with no domain adaptation, then we get segmentations like this one. But first, we transform these images and we make them all look like conic images and change the texture. Now the prediction looks like this. So by accounting for these discrepancies in the training and test set, then we can improve the performance. And again, I argue that this is a consequence of having a limited number of instances. There are many probes in the market, and it is going to be close to impossible to get a comprehensive data set from all the possible probes, mainly because there are probes coming out very frequently, new ones. Now, these results are not only visual, we can actually measure, for example, the dice score, and the dice of the red bone was 0.44, and of the blue one was 0.8 when we didn't do anything. Just by making this transformation, exactly the same data, exactly the same architecture, everything the same except the style transfer, we went from 0.44 to 0.64. It's an improvement of 20 points. And from 0.8 to 0.87, which is an improvement of 7 points in the dice score. So these are the three ideas that I wanted to talk about. And the final remarks are basically that the traditional machine learning assumptions are not always valid for the medical applications because of the labels. They can be unreliable, and because the data sets are not huge to cover all the cases that we might encounter during inference. So we can compensate for this lack of data by using expert knowledge. And here we presented two ideas. One is to incorporate this knowledge in the form of probabilistic labels, or to incorporate this knowledge directly into the model. The idea is that the model doesn't have to learn everything from scratch now, because we are giving very strong priors and additional information. It is very hard to create comprehensive data sets in the medical domain. So then the topic of domain adaptation becomes very important, because you will never have access to all the images of all the test data. So then we have to figure out how to make the model generalize better. So yeah, this is what my research is about. All of these topics are discussed in more detail in the dissertation, which you can read if you are interested. I recommend you not to, but you can do it. And yeah, that's it.
Thank you very much. I'm going to stop recording now, and then we can have questions. Thank you.